Welcome back, everyone. So in our previous session, we began to explore exponential functions. And so today we're going to take a deeper look into exponential functions. We're going to look at a specific type of exponential function. Okay, so today we're going to explore exponential growth equations. And so I want to just make a connection between our standard formula, which is y equals a times b to the x, and the formula for the exponential growth. All right, so I've kind of color coded it here so that it's a little easier for you to see. Remember that A is our initial value and B is our constant ratio between our successive outputs. Okay, and then X is our input and Y is our output. All right, so in a situation where we have an exponential growth equation, we still have that A is our initial value, right? So this is still our initial value. Okay, but now our B, which is our constant ratio, becomes 1 plus R. And this R is the rate at which our value grows. Okay, so, and notice that our B for our exponential growth equations will always be greater than 1. Okay, that's something that I want to point out. And then our input now becomes our time, because in any situation where we have exponential growth, we're going to have that our value is increasing at a certain rate over a unit of time. So it could be in minutes, it could be in years, it could be in hours. It all depends on the situation. All right, so now let's take a look at a specific situation where we have to figure out an exponential growth. All right, so we have a painting is sold for $1,400 and its value increases by 9% each year after it's sold. All right, write an exponential growth function to model this situation. And then we want to find the value of the painting in 25 years. We also want to graph the function, and we want to state the domain and range of the function. And we want to interpret what our y-intercept represents in our problem. Okay, so the first thing we want to do is we want to fill in this chart. So we're going to place 0 years, 1, 2, 3, and 4 years. All right, and so for 0 years, that would be when our painting is actually sold. And so our final value doesn't change. It's still going to be the $1,400. Okay, and then for 1 year, we are going to increase this $1,400 by 9%. Right, so we're going to increase this $1,400 by 9%. Okay, and let's make that decimal clear. And so if you notice, I wrote my percent as a decimal. When we're dealing with exponential growth and exponential decay, which we'll get into in a second, we change our percentage to a decimal or a fraction. So if you need to remind yourself of how to do that, for a fraction, it would be our percentage over 100. And then for a decimal, we place our decimal behind the first non-zero digit and move it 2 places to the left. Okay, so our value, so this is our increase by 9%, but that's not our total value. Our total value is going to be this increase plus the initial value that we had, which is $1,400. Okay, and so when we evaluate this expression, we're going to get that we have $1,526 or $1,526. Okay, and notice that these two terms have a common factor, right? So let's grab the highlighter, and I want to highlight that. It has 1,400 in common. So what we're going to do is we are going to use reverse distribution, which is called factoring, and you'll learn that when you get into Algebra 1 in 9th grade. Or actually when you get further into Algebra 1 with Ms. Quint, and you use it in Algebra 2 as well. So this is going to be, I'm going to pull that 1400 out, and I'm left with 0.09 plus 1. Okay? And so after 2 years, we're going to take this, our previous term, so now we're adding interest to this value, not to our original value. We're taking this value, and which is 1526, but I'm going to keep it as 1400 times 1 plus 0.09. And we're going to multiply that by 0.09 and add that to our initial value. All right, so again, I'm going to use up a little bit of space here. So let's go and let's take out 3 and let's take out 4. All right, because I want you to see this connection. All right, so again, we have a common factor of 1400. All right, so let's factor that out. And so we're going to have 1400 times 1 plus 0.09. And then we have this extra 0.09 out here. Plus, now if we factor out this 1400, so here we're left with 1. Okay, and so for our final expression, we get 1400 times 1 plus 0.09 to the second power. Because remember, if you take a number times itself, and remember addition is commutative, so these terms, these two expressions are the same. It's called squaring. All right, and so when we evaluate this, we get a value of $1,633.34. All right, and remember with these values, you want to round to the nearest cent because we're dealing with money. Okay, and so let's finally do it for 3. So I'm going to take this value, I'm going to multiply that by 0.09 because that's my rate of increase, and then I'm going to add that to my initial value to get my final value that I need for after 3 years. All right, and so again, common factor. Okay, and we're going to factor that out. And so we have 1 plus 0.09 times 0.09 plus 1. Okay, and so our final expression will be 1 plus 0.09 to the third power because we've added another term. Okay, and that value will be $1,813.04. Okay, and so if you notice, so let's highlight, let's use a different color. I'm going to use blue. So if you notice these highlighted expressions, okay, they are essentially written in the form of our exponential growth function. So we have a times 1 plus r to the t. Okay, and so in this case, our initial value is 1400. Our rate, or our growth rate, is 0.09, and our time, or the number of years, is t, is our exponent, and it increases by the same number of by the number of years. All right, so if we wanted to, let's slide the page down. So if we wanted to, I'm going to write my exponential function, which is going to be, I'm going to call it v of t for the value after a certain number of years. It's going to be 1400 times 1 plus 0.09 raised to the t. Okay, and if you wanted to add these two together, you get 1.09 raised to the t. Okay, so this is our exponential growth function for this situation. All right. And so I've already graphed it here for you so that the graph is clear and it's neat. And so now we want to evaluate this for 25 years. So we're going to replace our time with 25 years. Okay. And so when we do that, we get a value of $12,072.31. So that's our value after 25 years, or the value of the painting. All right. And so you can see that that is this point right here after 25 years. Okay. And so now they also asked us to state the domain and the range of this function. So remember, the domain is the set of input values that will work for this function or this situation. And so we can see that any time greater than 0 years or equal to 0 years actually works. So our domain, which I'm going to write as D, is going to be t greater than or equal to 0. And our range is all of the set of outputs that work for this function. So our range is going to go from, is going to be any value greater than our initial value, which is 1400. So any y greater than 1400 or equal to 1400. Okay, and so if you look, our y-intercept is this first point, because that's, remember, our y-intercept is where it crosses the y-axis, or where x is 0, is actually 1400. So the y-intercept is our initial value. Or our A. Okay? All right. So now let's go into exponential decay. All right, so exponential decay is not that different. And I want to point out that sometimes it would be called depreciation, but exponential decay is the opposite of exponential growth. It's when you have a quantity or a value that decreases by a certain rate over a unit of time. Okay, and so the only thing that changes with our function is that the plus becomes a minus, right? This is the only change from our exponential decay, is that the plus that's here becomes a minus. So instead of our b being greater than 1, our b is now always going to be less than 1. Okay. And so let's look at a situation that requires exponential decay. So the population of a town is decreasing at a rate of 1% per year. In 2005, there were 1,300 people. Write an exponential decay function to model this situation, then find the population in 2013. Graph the function. All right, so what we want to do is we want to grab our function. So it's a 1 minus r raised to the t. Okay, I'm not going to use the table here because you can refer back to the exponential growth to see how we arrived at this function. All right, and so we know that from our situation that our initial value in 2005 was 1,300 people. So that's going to be our A. And we know that our rate is decreasing at a rate of 1% every year. Okay, so that's going to be 0.01, and then we have some time. Okay, so we have this function, and now we want to find the population in 2013. Okay, so what we want to do is remember that our years are, which is t, we start with 0. So 0 represents 2005. So that should be represents 2005. So if I wanted to get to 2013, that's going to be a jump of 8 years, right? So our t would be 8 in this case. So we want to find 8, the value for 8. So 0 was 1,300, and we want to find the value for 8. So that means we're going to substitute 8 for t. So we get that this is 1 minus 0.01, or this is 0.09 if we subtract these two, raised to the 8th power. And so y I'm going to write of 8 is going to be evaluating this expression, which gives us approximately 1,200 people. Okay, and so now we want to, I'm gonna leave the graph of this function to you. All right, so what I want you to do is in your notes, find the value, the number of people, people in the population for the values of 1, 2, 3, and 4, and then you can graph those. So 0, you already know. 1, 2, 3, 4, you can graph those. Okay? Okay, so in our final situation, we have this graph that shows the value of 2 different shares of stocks over a period of 4 years. And so what we want to do is we see that the values have been changing exponentially. And for each stock, we want to write an equation, an exponential equation, that represents the value of this stock over this time. Okay, so let's begin with the first one. So I'm going to write, I'm going to separate this. I'm going to write stock A, and I'm going to write stock B over here, right? So that we can keep our equations separate. Okay, so stock A, in this case, we have to pull this data from this graph to see if, to figure out how we can find out this exponential function. All right, so for stock, let's start with stock A. We see that we have a y-intercept of 16. Okay, so we have a y-intercept of 16, and then we see that it intersects, or let's grab another point off this line. So I'm going to pick this point right here, which is going to be 112. Okay, and I'm going to pick this point 112. So that means that after 1 year, the value of stock A was $12. Okay, so if you remember from our previous example, we said that the y-intercept represented the initial value. So we can, for stock A, let's say y of t, because we're dealing with time in years, is going to be, the initial value we know is going to be 16. And then we need to find out our, basically our rate, or our growth rate. Okay, so in this case, what I'm going to do is I'm going to use a table. If you remember from our previous lesson, when we first looked at exponential functions, we could find our b, the value of b, from taking 2 successive points. So if we have 0, 16 and 112, then our b is going to be 12 over 16, which if we reduce that, we get 3 over 4. Okay, so this is 0.75. All right, and so for stock B, we're going to do the same thing. So here we see that our y-intercept is 4. And if we grab another point, let's grab this point right here. So that's 1, and this is 4, that's 1, 6. Okay, because it's going up by 2s. So 1, 6. So again, we have y of t, or let's say y prime of t, to differentiate the 2 stocks. And so our initial value here is 4. And now we need to find out the value of b here as well. So we're going to do another table. And we're going to have 0, 4. And our second point was 1, 6. And so the value of b here is going to be 6 over 4, which when reduced gives us 3 halves. So that's 1.5. Okay, so we have these two exponential functions for our values for our stocks, stock A and stock B. And they want us to describe and compare the behaviors. Okay, so what we can say is we automatically know from our graph. So let's look back at our graph. We automatically know that stock A is decreasing over this period of 4 years, and stock B is increasing. Okay, so we can say that stock A is exponential decay. And so I'm just going to write this out. You can write it, when you write it in your notes, you're going to write in full sentences. So exponential decay, and stock B is exponential growth. Okay, and we also know that from our y-intercepts, our initial value of stock A is $16. It started at $16, their value. And for stock B, the initial value started at $4. Okay, so make note of that as well. And finally, we know that after 2.5 years, so here, after 2.5 years, both stocks will be worth the same value, which is $8. Okay, so after 2.5 years, A and B will be worth the same value. Okay, and that is the end of today's lesson.